All right, let's talk about potential energy. Now, potential energy is the energy possessed by an object by virtue of its location. So there are going to be multiple different forms of potential energy, but we're only going to focus on two of them. Now, your two most common forms of potential energy are your gravitational potential energy and your elastic potential energy. Now, all potential energy is going to be represented by the variable capital U, right? And the subscript will tell you what type of potential energy you're dealing with. So U sub G would be gravitational potential energy, U sub S would be elastic potential energy. Now, the reason we call it potential energy is because it's energy that has the potential to be converted into other forms of energy, whether we're talking about kinetic energy or thermal energy, which is heat. Um, so that's the reason for the term potential. Now, potential energy, just like kinetic energy and work, is going to be measured in joules. Um, so let's take a look at gravitational potential energy first. That's going to be the primary one you're dealing with. Um, Most of your conservation of energy problems that we'll get to in the next lecture deal with gravitational potential energy. But your gravitational potential energy is equal to mgh. So it depends on the mass of the object and it depends on its height. Now, one thing to be um, cognizant of is that when we're talking about height, height is entirely arbitrary, right? It depends on the observer himself. So let's say we were in a year where we could do labs, and we're in a lab out in the hallway dropping a ball. Well, where would be the most logical place to set height equal to zero at? Well, it would be the floor, right? But let's say we were doing that same lab inside the class, and rather than dropping it on the floor, we were dropping it on the lab tables. Well, at that point, height equal to zero would best make sense as being the surface of the lab table, right? So where you set height equal to zero is entirely up to you. And that will come in handy with some of these problems because you can adjust where you set height equal to zero to make your math easier. And again, the reason we can do that, we talked about it a little bit when we talked about kinetic energy, is because there really is no one true level of energy for an object, right? Because it all depends on what the observer is doing, right? And so we don't necessarily care about an absolute truth as far as the energy level is concerned. What we care about are differences in energy levels. And so that's why we're able to do that. Right? There's no one place in the universe where a sign is stuck that said, here height equals zero. Right? It's all dependent on who's observing, where you located, that sort of thing. Now, also keep in mind, we talked about the work energy theorem as being work is equal to a change in kinetic, but really, work is a change in any type of energy. Now, typically we define it as this because usually you're dealing with it in terms of kinetic energy. But take, for instance, let's say there's a book laying on the floor. You lift that book up 1 meter. Well, that book's potential energy changed, right? Well, why did its energy change? Because you exerted a force that did work on the book that increases potential energy, right? So, work done on this book increases potential. Now, one other thing to keep in mind when we're talking about changes in gravitational potential energy is that it's entirely path independent. So if you look at example 10.7 of these people racing up a skyscraper, yeah, they're taking a spiral course up that skyscraper, but that doesn't matter. All we care about in changes of gravitational potential energy is what altitude did they start at, what altitude did they finish at, right? So all we care about is that vertical displacement. We don't care about the actual path they took because it's path independent. So since we're looking at 10.7, let's go ahead and go over it. So these people are running up the Empire State Building. They climb a total vertical distance of 320 meters. We want to know how much gravitational potential energy does a 70-kilogram racer gain during this race. So let's just start by listing out what we know. So the mass is 70 kilograms. The height that they ascend is 320 meters. we know G, and we want to know the gravitational potential. So gravitational potential energy is equal to mass times acceleration due to gravity times height. So gravitational potential energy is equal to 70 kilograms times acceleration due to gravity times 320 meters. So your gravitational potential energy comes out to 219,520 joules. Now, take a look at Stop to Think 10.4. In this scenario, we've got 4 identical spheres. So they have the same mass, and they're all at different heights. And we want to rank their gravitational potential energies from largest to smallest. So take a second, pause the video, see if you can't figure that out. Alright, so they all have identical masses. They're all on the same planet, so they're all experiencing the same acceleration due to gravity. So we know that 3 has the most gravitational potential energy. Now, where most people, or where a good number of first level physics students go wrong, is looking at 2 and 4. Now, 2 has identical potential energy as 4 does. Right? It doesn't matter what their overall direction of travel is. We're looking at that one snapshot moment in time. And at that one moment in time, both of them have the same mass and they have the same height. Right? Yes, they'll have different potential energies in the next second, but we're just looking at that one moment in time. So it doesn't matter, one's going up, one's going down. It doesn't matter what happened the second before, what happens the second after. All we care about is that 1 second. And then lastly, 1. Alright, so the second most common form of potential energy you're going to see is spring potential energy. And spring potential energy is equal to 1/2 kx squared. Now, k is something new we haven't seen. And k is what we call the spring constant. And the spring constant is going to be measured in newtons per meter. Now, be careful with the term spring constant. Spring constant kind of implies that it's constant universally. That's not true. The spring constant is constant to that individual spring. So whether you're compressing at 5 centimeters, 10 centimeters, stretching at 5 centimeters, stretching at 10 centimeters, doesn't matter. That spring constant is constant for that one individual spring. And so when we talk about spring potential energy, what you're talking about is energy that's stored within a spring or any other elastic material, whether it's the drawstring of a bow or a bungee cord. Anything that is elastic falls under spring potential energy. We'll often call it elastic potential energy as well, so those two terms are interchangeable, so keep that in mind. Now, notice, if we go back to the spring constant, that the unit is newtons per meter. So let's say that you've got a spring constant of 300 newtons per meter. What that's telling you is that it takes 300 newtons of force to compress or stretch that elastic material by 1 meter. Now, if we look back at that equation, the x in that equation is your compression or stretch distance off of equilibrium. Now, what do we mean by equilibrium? If you take a look at the photo in the notes, well, every elastic material, be it a bungee cord or a spring, is going to have some certain length that it has when no force is being applied to it. And that's what we call its equilibrium position. So x represents how far off of equilibrium you either compress it or you stretch it if you're going the other way. So x is just determining how far off of equilibrium you've pushed it or pulled it. Now, one thing we didn't go over in forces that I like to save till now is Hooke's law, and Hooke's law is often going to be used in conjunction with your elastic potential energy equation. And Hooke's law tells us that a spring force is equal to the spring constant times the distance to which it's either compressed or stretched. So make sure you've got Hooke's law in there because, again, this comes in quite frequently when we're dealing with spring potential energy. So let's take a look at example 10.8 together. In 10.8, we got an archer pulls back the string on her bow to a distance of 70 centimeters from its equilibrium position. To hold the string at this point takes a force of 140 newtons. How much elastic potential energy is stored in the bow? Well, let's start by just listing all of our knowns and unknowns. So the archer pulls that bow back by 0.7 meters. It takes a force of 140 newtons to compress at that distance, or sorry, to stretch at that distance. And we want to know how much elastic energy is possessed by the bow. Well, first thing we're going to need to know if we want to find our elastic potential energy is we're going to have to know the spring constant associated with that drawstring. So we can use Hooke's law to determine that. So the force of 140 newtons is required to pull this string back 0.7 meters, which means that K comes out to 200 newtons per meter. So it takes 200 newtons worth of force to pull that drawstring by 1 meter. So now we've got enough information to solve out for our elastic potential energy. So 1/2 of 200 newtons per meter times 0.7 meters squared. So we get an elastic potential energy of 49 joules. Now lastly, take a look at Stop to Think 10.5. We got a spring, it's stretched by 5 centimeters, its elastic potential energy is 1 joule. What will be its elastic potential energy if it's compressed by 10 centimeters? So take a few minutes, pause the video, see if you can't figure that out. Alright, a good place to start would be, let's find the spring constant. So, if we look at our elastic potential energy equation, we know that there's 1 joule of energy when you compress that spring, when you stretch that spring by 0.05 meters. So K here, K comes out to 800 newtons per meter. So we've got that same spring being compressed by 10 centimeters now, and we want to know the new elastic potential energy. So 1/2, oops, there should be K there, of 800 newtons per meter, because again, that spring constant is constant for that spring, times 0.1 meter squared. So your spring potential energy comes out to 4 joules. Right, so the answer would be D. Now I'm uploading 5 fairly basic potential energy questions. So knock those out, submit them when complete. Those will be ones that contribute to that overall 6 formative grade. And then the next thing we'll be covering is conservation of energy. Conservation of energy we're going to cover all next week and most of the week after that. Plan tentatively on testing at the end of the week after next. So that would be the week, let's see, plan tentatively testing on the 28th, 29th area of January. So, um, hope that helps. Come to live sessions and we can talk about this in more detail. All right, take it easy.